In this video, we're going to try and figure out what exactly would be a growth function for the Tower of Hanoi's pseudocode algorithm that we gave before. So that same code is on the right-hand side. Let's try analyzing it. So what we want to write is an f and n function where n is the number of disks, right? That's our problem size. And the result of it, right, f of n itself, is the number of moves that are required to get there. So think about this for yourself for a second. What would f of 1 be? What might that be set equal to? So think about that. So that's actually going to be set equal to 1. And where that comes from is we see that, okay, f of 1, right, corresponds to this over here, right? N is equal to 1. The algorithm says do this. Do this happens to be make one move. So that one move that's made, that is what should be used, right, for our f of 1 function, right? So f of 1 equal 1, right? When the tower is 1 high, I make one move. Right? That's the easy one. What about the harder one? How could f of n be written? Think about that for 1 second. Right? This is the more general case, right? This is the case that involves the recursive steps. So that'll be a little bit more tricky. That'll be f of n equal 2 f of n minus 1 plus 1. So these lines of code here, right? I have 3 lines of code. The first line of code, right, is moving a size n minus 1 tower. So that'll cost me f of n minus 1. But then I move a second tower, also of size n minus 1. That'll also cost me f of n minus 1 size. F of n minus 1 moves. So there, right, that's what gets me this term in front over here, right? The 2f of n minus 1. Gets over here, it looks like I forgot to my 1, so let me add that in there. And then the plus 1 comes from the fact that I have one move that has to happen here. So that ends up getting me that plus 1 there at the end. Okay, so that's what we have. F of 1 equal 1, f of n equal to f of n minus 1 plus 1. So that's what we have. And it's great because it gives us the right answer, but it's not great because it's an open solution, right? I still have this recurrence there where every time I want to evaluate something, I need to evaluate, lesser value, lesser value. So it makes me hard, basically, it makes it difficult for me to use this function. So what I'd like to do is try and guess from that a closed loop function, right, or a closed form function for it. And we'll just do this purely by guessing, which is something that'll work if we're very, very lucky, which isn't very common. So we can just be happy, though, for this. For this example, we can be happy, right, that we can do it this way, but it won't always be the case. So what we could do, right, is we could calculate out by hand some values for f of n. And so by hand, I don't really mean, on a piece of paper, but throw it in Excel, right? Always, if you have tools for something, use the tools, right? Make your life easier. Don't make your life harder. So over here, right, we have our column here, right? On the first column, I have a table. First column I have is basically n, right? Problem size. The next thing I have is actually the evaluation of our function that we figured out earlier, right? Our f of n equal to f of n minus 1 plus 1. I have the evaluation of that. Right, so I can kind of put these side by side. So ideally what I would have is I would have a very simple function that would take in n and then would produce the values on the right hand side. Right, so it's something that takes in 10 and then returns 1023. That's what I would like. That's what I really, really want. Here you might notice there's a little bit of a pattern. There's actually something that looks like a power 2 number emerging on the right hand side. This is actually an exponential time algorithm, by the way. It takes a really, really long time to run. Actually, yeah, maybe ask yourself for a second. Why might it look like a power of 2? Why? Maybe go back and look at the code for a second. Why might this look like a power of 2? Actually, it's not so bad here. The reason it looks like it's power of 2 is because it makes 2 recursive calls. So every time you run it, it doubles the amount of work it has to do. So if you're doubling, well, that's like a power of 2. So we have something that looks like 2 to the n. Okay. So on the right-hand side, maybe from that kind of sequence, you would guess that, hey, f of n looks like 2 to the n. So we might think that for starters, right? F of n equals 2 to the n, and then it looks like each of these numbers is off by 1, so let's throw a negative 1 in there as well. So our proposal would be from this chart, just guessing a pattern, that f of n equal to n minus 1. This would be our guess. So that's great. But, of course, there's a little snag here. That is a guess. and the guess really isn't what we need. We want to be right. We want to write a growth function that we know for absolute certain is the correct growth function. Because it could be the case that when n becomes really large, oh hey, all of a sudden those things don't match up, right? Our f of n computed recursively doesn't have the same value as this 2 to the n minus 1 that we're guessing, right? That could happen. I don't have any evidence, right? My chart only goes up so far. It only goes up to 16. Beyond that, I don't have any evidence that this thing is actually correct. So in order to do that, right, in order to verify that this function is actually correct and that it does actually match the recurrence, we're going to have to break out induction. Okay? So in the next video, what we're going to talk through is proving mathematically that these two functions, right, the f of n 2 to the n minus 1 and f of n equal to f of n minus 1 plus 1 are the same. And we'll do that using induction. So we'll do that next. It will be a little bit involved from kind of the technical mathy perspective.